So another thing that we can take away from these substitution reactions and the introduction of this lecture material is that number one, we are organic creatures. So substitution reactions, they're not uncommon in our biological activities from a day-to-day basis. We do have substitution reactions that go on the inside of us from minute to minute, from second to second. And one of the always questions that people ask is, well, carbon is in this group 4, and there's other elements in group 4 as well. So we are carbon-based compounds. And not only that, but yeah, it is true that we do have carbon, but there's some other compounds or some other elements that really make us up to who we are today as well. Carbon's not the only one. It's not uncommon for us to have oxygen, so we see oxygen scattered throughout our system, throughout our biological molecules, throughout our reactions. We need oxygen in order to breathe and live. So oxygen is a very important key player as well as carbon. We also see nitrogen being very common in our human system as well. So nitrogen and nitrogen containing compounds, these are going to be very important. Nitrogen containing compounds, these are things like amino acids, right? And I see the word amino and I think of the word amine, so therefore these compounds probably have nitrogen in them, and they do. The amino acids make up basically our proteins and our muscle and everything else that comes suit with the amino acid groups. So we've got carbon, we've got oxygen, we've got nitrogen, and of course we have hydrogen as well. Hydrogen is very common in organics. We see hydrogens loaded on these molecules and on these structures, and they just really help satisfy all of the octet and everything else that these molecules require. Okay, so they're very well suited. They work hand in hand together. There's really no issue. They get along great, so they hardly ever fight. It's a very good family. However, this is carbon containing compounds. Well, does silicon really behave the same way? If I take a look at the periodic table, silicon is kind of below carbon. And silicon below carbon, it's in the same group. So carbon and oxygen and nitrogen and hydrogen have this nice friendly relationship. Well, does silicon have the same friendly relationship? And the answer is yes, it does. So we can see silicon and oxygen bind up, we can see silicon and nitrogen, we can see silicon and hydrogen, we can see a mixture of all of them, but silicon is another one of these elements that's very similar to carbon. It has the same number of valence that carbon does. The only difference is that silicon is a little bit larger. And because it's a little bit larger, it gives us weaker bonds. Okay, and that's bad news. If I'm looking at, structures of sugars and amino acids and fats and things that really help me run on a daily basis, if I look at DNA molecules and realize how stable those things have to be, then weak bonds are bad news. We do not want weak bonds if we can help it. So if we switch over to a silicon-based organic creature, that silicon will give us weaker bonds versus something like carbon, and that could lead to disaster down the road. So off of this comes the whole discussion of availability. If you look at the crust of the Earth, you're going to see silicon has a higher percentage than actually carbon. So when we first were formed, even though silicon was around a little bit more, we were smart enough not to go for what we had the most of. We were smart enough to go for what element will give us the most stable bonding, because that stable bonding will lead to stable creatures such as ourselves. Hopefully, at least I can speak for myself. I don't know about you. So because silicon has weaker bonds, then it actually participates in substitution reactions a little bit better. And that's bad news for us because we don't really want what should be stable molecules participating in substitution reactions every time they get a chance. So for that reason, silicon is bad news just because it could be a little bit more reactive in the substitution world versus a carbon-based compound instead of a silicon-based compound. Not only that, but carbon gives rise to a product, an end product in the metabolism route known as CO2. Well, silicon, if we used it as a silicon-based compound instead of a carbon-based compound, would give rise to a metabolism product known as SiO2. And SiO2 can polymerize. And polymerization is bad when it concerns SiO2 because this is known as sand. So instead of breathing out CO2 as a byproduct from the metabolism, we would be breathing out sand all over the place as a byproduct from the metabolism. So a couple of reasons why silicon-based compounds just won't really make sense versus something like a carbon-based compound. Carbon-based compounds are a little bit more stable. They allow reactions to take place, but they're a little bit resistant to them because they have to be kind of coached into them beforehand versus something like silicon that would just be willing to participate at any time and any point whenever it can. And then finally, just in the metabolism process itself, what are some of the byproducts that come from these reactions? And one of those would be problematic for us if we were silicon. I mean, could you imagine walking on beds of sand all over the place, or people sweeping up sand because you were breathing out too much of it? So again, we are carbon-based compounds. There is a reason for it, and these are just a couple of the reasons. And we can really meld the substitution reaction description into that description as well.